Yeah, so we finally reached the last part of lecture 5 and perhaps the most interesting one, scikit-learn pipelines. So scikit-learn pipelines are objects or classes that let us join together data processing and prediction steps, which makes them very useful in practice. So here's an outline, a flowchart of how pipelines work. I won't go over all the details now. I will show you this flowchart again after I showed you an example of a pipeline. But in a way, you can think of a pipeline as estimator and transformer API. So you again have a fit method that you can use on the training set, and then after that, internally what will happen is there will be several fit and transform steps and the final fit step, and depending on what's in your pipeline, you can define what's in your pipeline. It can do, for example, data scaling like standardization or min-max scaling, or dimensionality reduction, and then training a learning algorithm, and then returning a predictive model that you can then use to operate on the test set. So when you then give it the test set and call predict, similar to the estimator API, it will internally use a transform to carry out all the scaling that was carried out on the training set, and then also do the final prediction to, for example, return class labels if our predictive model is a classifier. But we will take a look at this again in a few moments after I showed you a very simple code example of a pipeline. So here I'm creating a pipeline using the make pipeline function from scikit-learn's sklearn.pipeline submodule. There are different ways you can create pipelines. Similar to an estimator, you can also call or create a pipeline using the pipeline class. However, I think this is maybe the more convenient way of creating a pipeline. So how that works is that you provide the initial components of a pipeline. In this case, it's a very simple very simple pipeline consisting of a classifier and a standard scaler. So the standard scaler is what we talked about in the previous video, that standardizes the data so that it has zero mean and unit variance. So we have the standard scaler here, and then we have a learning algorithm, the k-nearest neighbor classifier, that will then be a learning algorithm that will result in a fitted model. And by just executing pipe, or you can also say print pipe, you will see the initial steps now listed here. And this is a class, pipeline class then. So it will return a pipeline class. Yeah, then after we created the pipeline, we can use fit to fit the pipeline on the training data, and then we can use predict to make predictions on the test set. So what happens if we call fit? If we call fit, it will call fit using the standard scaler first. So the standard scaler, remember, will learn the mean and the standard deviation from the training data, and then it will use those to scale the data. So there will be a standard scaler will do a fit and a transform, and then here, so the standard scaler, when we call it in a pipeline during fit, it will then return the scaled data and feed it to the next step, and the next step is the k-nearest neighbor classifier. So the k-nearest neighbor classifier will receive standardized data. So it's basically doing two things in one. Instead of initializing a standard scaler, then fitting the standard scaler on the training data, and then having scaled data via SC transform X train, and then having the KNN model. Let's say I initialize it already. Here, and that we fit on the scaled training data. So instead of doing these 4 steps separately, the pipe.fit will already do all these steps for us so that the KNN receives the standardized training set. for learning, and then during prediction the same thing happens, except of course there won't be a fit. So during testing we will reuse the standard scaler from training and then scale the test data and give the test data to the KNN while it's now doing prediction. That would happen for the test data if we call predict. But I think now this is easier to explain if I use my flowchart again. So here in the flowchart, it's again highlighting what's going on. So you as the user, you only use fit and predict. So you use fit to fit the training set, and then you call predict to use the parameters like the scaling learned from the training set and the predictive model learned from the training set to make predictions. And also note that you call fit, but internally the pipeline will call also transform. So there's one convention in a pipeline that the last step is the classifier. So the last step is a learning algorithm or object like the k-nearest neighbor classifier here. And this last step will only call fit, but all the other steps in between will call fit and transform. So you can't have like two classifiers in this pipeline. Only the last element, in this case we only have two elements, only the last element can be a classifier, and the previous steps have to support transform. So it could be, for example, the standard scaler that you can use here. Instead of using a standard scaler, you can use a min-max scaler, for example. You can also add certain dimensionality reduction techniques. We will talk more about that later in this course. But one common dimensionality reduction technique that some people use often with k-nearest neighbors is principal component analysis, or in short, PCA. So PCA would be a linear transformation of your data that, for example, you can apply to a large dimensional data set and it would return a smaller dimensional data set. So you can also have that here, and you can have an arbitrary number of transformers here. The only thing is that they have to support fit and transform. And then after fitting, when you call predict, the pipeline will only call transform on the scalars. This is related to what I explained in the last lecture, that we reuse the training set parameters when we scale test set, because we treat the test set as unseen new data. So instead of test set, it could also be just one new training example, or one more data instance, one more observation. So it could be just new data. So if you, for example, deploy your model on a web server and you have a new customer and you want to do a certain prediction, what movie the customer likes, for example, then you can also use the pipeline. It would do a predict, transform. So transforming, if you did a standardization during training, this would also then use the standard scaler with a mean and standard deviation from the training set. And then if you used dimensionality reduction, we'll also do that. And then finally call predict on the classifier to return the class labels. Yeah, and that's essentially a pipeline. It allows us to chain together multiple objects like transformers and estimators. Yeah, let's see a pipeline in action in the context of simple model selection using the what I call simple holdout method, because that's the simplest form of model selection. Later in this class, we will see many other methods for model selection, such as k-fold cross-validation and so forth. But yeah, I don't want to stuff too much here into this lecture because it's already a very long lecture. So model selection will be a topic for another day. Any case, so the holdout method here is just a way I want to just briefly demonstrate the pipeline in the context of hyperparameter tuning. So model selection is basically a fancy word for hyperparameter tuning and selecting the best model that comes out of the hyperparameter tuning. So what we have here is we have the data set that we split into a training set and a test set. So then I'm splitting the training set further into the test set that we are going to use for the learning, and then a validation set where we evaluate our model during training. So it's not exactly during training, but what we do is we train multiple models using different hyperparameter settings, and then we evaluate the models on the validation set, and then we pick the best one. So, for example, consider the machine learning algorithm as the k-nearest neighbor algorithm. And for each round, we choose hyperparameters. For example, it could be k equals 3, k equals 5, k equals 7, and so forth. And in each round, we fit the model on the training set. And this model that comes out of it, from the fitting, we evaluate on the validation set. So we do that many times. And then based on the best validation set performance, we pick that model and use the test set and then evaluate that model. Because if we do hyperparameter tuning, we reuse the training set multiple times and we use the same validation set multiple times. So it's not an independent set. So the validation set is not independent because we reuse it over and over and over again. So it can be a little bit over optimistic. So if we get an accuracy, let's say, I don't know, some values here, 80% on the training set, we often find that the validation set performance will be lower. Let's say it will be 73% prediction accuracy. And that is just because of overfitting. There's usually always some degree of overfitting. There are ways we can improve upon overfitting, and we will talk about that in the model selection lecture later on in this class. Now, if we do the hyperparameter selection on many different hyperparameters, if we do the model selection with many different hyperparameters, this is maybe just the best model that comes out of it. There are many other models, like 63%, 68%, and stuff like that. But even if we find here the best one on the validation set, it's kind of over optimistic because it can be just due to chance that this one just performed best on this particular data set split. But then we have an independent test set where we can get the performance on data that was not involved into tweaking and model training and tweaking and so forth. And often in practice, we would observe that the test set performance is also a little bit lower than the validation set performance, like some maybe 70% here or something like that. So usually you find it's also slightly lower, but it depends, of course, how often and how extensively we used the validation set. In any case, so this is the outline of the simple holdout method. And we are going to do the holdout method now in scikit-learn together with a method called grid search. So grid search is a hyperparameter tuning approach. So as the name grid implies, it will create a parameter grid. So for example, consider the case where we only have 2 parameters, otherwise it would be a hypercube grid. So if we have k nearest neighbors with k and let's say p as in the Minkowski distance. So for p we maybe have only 2 values, or we consider only 2 values, 1 and 2. And for k we can consider, let's say, 3, 4, 5, 6, 7, 8. And what grid search will do, it will just simply iterate over all these hyperparameter combinations. So it would evaluate p equals 1 and k equals 3. So this would be p equals 1, k equals 3, and then p equals 2 and k equals 3, and so forth. So it would consider all the possible combinations here. So if I only have 1, 2, 3, 4, 5, 6, and 2 here, so in this case I only have 6 times 2 combinations, so I only have 12 hyperparameter combinations. But let's say I add another hyperparameter with, 5 possible values, then I would multiply the 12 by 5, right? So in that way I would have then 60 already. And you can see the more hyperparameters you have, the more expensive this method becomes, and it grows polynomially in polynomial time. For example, if you for each hyperparameter only consider 5 possible values, and you have, let's pick a letter that we are not using here. Let's say you use t hyperparameters, different hyperparameters to tune. So you would have 5 to the power of t things you have to evaluate, right? So if t equals 1 or 2, that's manageable. That's either 5 and 25 then. For 3, you have 5 to the power of 3, which is 75, right? But then you can see how that grows. It will grow pretty fast, so the number of things to evaluate. But for this purpose, it's just fine. It's a small grid, right? So that's not a problem here. So, unfortunately, the grid search CV by default is a little bit trickier to use for the holdout method compared to k-fold cross-validation. So we have to do some manual tweaking, which is maybe why it looks so much more complicated than it could be. So what we are doing is we are using this predefined holdout split here, which is a method that will just return the indices for a training set and a validation set, given all the indices in the data set. And now for this simplicity here, also assume we have a separate test set tucked away somewhere. So yeah, again, here we created our training indices and validation indices. Now let's get to the pipeline part. So we have make pipeline here, which returns the pipeline. Then we define a parameter grid that we want to consider. This is for the grid search, the hyperparameter search or tuning. And we then provide the indices to the predefined holdout split method, which is just the way for splitting the data in the grid search. So later on in this course, instead of using this split object, we will provide values like 2, 3, 4, 5, and so forth. And this will be then, if we provide integers, will be k-fold cross-validation. So 2 would be then two-fold cross-validation, which is a little bit different from the holdout method. It looks very similar. However, it will be exactly a 50-50% split of a data set. So it will be splitting in the middle, and it will also then rotate at one time. So here in this simple holdout method, we don't rotate anything. We just have a validation set and a training set, which is why we have to use this little workaround using the predefined holdout split with these indices. In any case, there's maybe too much detail. Maybe ignore even the predefined holdout split here. For now, it's something you probably won't use in practice. So what's more important here is the pipeline and the hyperparameter grid, and then grid search CV will do the hyperparameter search for us. So here it is how it would look like in action. So these two panels are from the previous slide. So once we call grid.fit, it will run the hyperparameter tuning, and after that you can see there will be an attribute available called CV results._, and like we discussed earlier in scikit-learn, the convention is that these attributes with a trailing underscore are only available after we call .fit. So fit in this case will run the grid search. And the results contain a lot of information, and not all of that is always useful. I mean, it's always nice to have as much information as possible, but what we usually care about is the parameters and the associated scores. So here we have something called params, which are just the different hyperparameter combinations. It's a little bit unfortunate. This would be better on this line. It would be easier to see then. We have 1, 2, 3, 4, 5, 6 hyperparameter combinations, because we had 2 values for p and 3 values for the n neighbors. So we had 3 times 2 equals 6 hyperparameter combinations. And these are all the possible combinations here listed. And then we would have the corresponding scores in an array called mean test score. The reason why it's called mean is that usually we use grid search with k-fold cross-validation, where we have multiple folds. But we will talk about k-fold cross-validation another day when we talk about model evaluation in more detail. So here the mean, there is no mean because we only have one validation set, so we don't average over data sets. So for this case, just maybe ignore the mean here. And then we can see the score here. The array has the same number of elements as the number of hyperparameter combinations. So then we can see for each hyperparameter combination the associated prediction accuracy. So by default, I should say grid search uses the prediction accuracy for classifiers, but we can also specify what score we use. But again, this is too much detail here at this point. Here, just assume it's the classification accuracy. And just to make this a little bit easier to see, I'm just iterating over them using zip. So I'm iterating over the parameter combinations and the scores. So you can see what the hyperparameter combinations yield in terms of scores. So you can see the two highest scores are 69% prediction accuracy, and that is for 1 nearest neighbor and 3 nearest neighbor. And it's for the Euclidean distance and here the Manhattan distance. So both give equally good results in this data set. on this validation dataset. Now, for convenience in practice, we usually don't even need to look at the scores. There's also an attribute called best score and the associated best params, which will give us the best score and the best parameters. And here I see it's neighbors 1 and neighbors classifier 2. So I assume the way they resolve the tie here is just by picking the first one, because we have a tie here. But since we already talked about grid search briefly, 2 more related topics. There's also a randomized search, which may be more efficient in practice, because in grid search, we sometimes evaluate like these combinations that are not good. So if we have a very large grid, let's say multiple dimensions, but I can't draw multiple dimensions, but let's say we have P 1, 2, 3, 4, 5, and so forth, and we have k nearest neighbors with k 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. If we have a very large grid, so it will iteratively run through this grid, right? However, if, for example, we know that for certain values here, 7, 8, 9. So if you go higher with the number of neighbors, it doesn't really improve for these here. It's also unlikely that for other distances that 7, 8, 9, 10 is a good choice. So maybe we're wasting a lot of time by always evaluating these here. So that way it can be sometimes a little wasteful and can take a long time to evaluate the whole grid. So randomized search is an alternative method where we still have a grid, but we would randomly pick points on the grid. So in that way, in shorter time, you get a better list of evaluated hyperparameter combinations, because here you really go sequentially, and let's say you're running out of time or something like that, you will have never tested something below here if you abort it early, for example, whereas with randomized search it will just keep going, and you can, instead of defining the hyperparameter range, you define the distributions, and it will randomly sample then from the distribution for an iter, where this is the number of iterations. You can say, maybe I only have like an hour or something like time, so maybe I will just set that to 100 or something like that, so to have that finish in a reasonable time. But if I'm in a hurry, I can maybe leave 10, which is super quick. If I have a day or something like that, I can maybe set that to 10,000. So instead of specifying a grid, we are defining distributions that it can sample from. So for more detail, you can then also go to the documentation, scikit-learn, but for right now that would be maybe too much detail. Okay, but now the really last topic for today is successive halving, and I'm just only mentioning it because I saw it the other day. It's a concept related to randomized search. It's taking it one step further. So in randomized search, we are having the random models or random hyperparameter combinations, and in successive halving there will be time steps where at each time step we eliminate the worst half of the models, and then we keep going with the rest of the models. This is maybe a little bit unintuitive in the context of k-nearest neighbors, but there are also certain methods that have a partial fit method, neural networks or things that get trained iteratively, like logistic regression. We won't talk about them in this class. However, there are methods that are successively fit, so you can do partial fits. And I will provide you also maybe with a chapter from my book where I did that, so you can update a model. And in that way, let's assume there's a lot of steps that it takes to fit a model. It would be very expensive to run the whole pipeline for the whole model, like over multiple partial fit calls. So what you would do is you would train the models for 5 minutes or something, and then you would eliminate the first half models, and then you would keep going, training the remainder, the best half, for another 5 minutes, and then you look at the remaining models again, and then again eliminate the worst half, and so forth. So you iteratively get rid of the worst half of the models until you only have the best models available. And the idea is basically that you avoid wasting time on models that are not good to begin with. But yeah, this was also just merged into scikit-learn. It's not in the release version yet, so it's nothing you can use right now. So you don't even have to worry about that. It's something you can just check out some time in the future, half a year from now on or something like that. Yeah, it was a very long lecture already, so I don't want to keep adding to it. One last thing, I don't include that in the slides here because it's just too much time-wise. But one last thing is I made a bonus notebook about column transformers. So that is, for example, if you have a data set with these different columns. Let's say this is my data set with different columns. One column is categorical and you want to use the label encoder. But in other columns, for example, here and here, you have continuous values that you want to standardize. So here you want to use the standard scalar, but you don't want to use the standard scalar on other columns. So in that way, how can you define a pipeline where certain transformers of the pipeline only run on certain columns? So by that, you can use a column transformer and apply it to such a heterogeneous data set where the columns have different types and you want to perform different transformation techniques in the different columns. So I made a notebook example for that. So you can, if you have such a case, you can read through this. So if you have in a class project in yours, have some case like that, that might be a useful notebook for you to check out.